Welcome, Marco Zennaro, and from Italy, Trieste.
Thank you very much, Frederick. Thank you very much for the invitation, and I'm super happy to be here.
Yeah, and why are you here today?
Yeah, okay. So I'm a researcher in an institution which is called the Abdus Salam International Center for Theoretical Physics. I'm part of a unit which is called Science, Technology, and Innovation. And part of the activity of this unit is in the field of IoT. So I have been doing IoT for long, since my PhD. And yeah, thank you
Yeah, and you did
a
your
lot for the invitation.
PhD in Sweden, didn't you?
At KTH, exactly.
Yeah.
Yes. So I can say, hey, that's my Swedish knowledge.
Oh, that's you come a far way with just that. So, but I mean, Sweden is special in that case. You can live in Sweden, you never have to learn Swedish. At least if you live in the large cities. I guess that applies for many countries. But yeah. So today, the topic for today, we are going to talk about wireless technologies in IoT.
Exactly. Yes.
Yeah.
I called it communication options.
Yeah, and probably a better word. So it was my topic. I reframed it. So, and to those of you that are following along now, we are going to keep the questions and everything in Discord. I'll write that on a ticker, chat in Discord. See. So please follow along and ask questions. I do have my eyes on both, and it's if you focus on talking, and I can focus on asking the questions for you, Marco. But if it's fine if you also follow Discord. So
okay.
But yeah, but we're going to talk about IoT and communications. So let's start with that.
Yeah. Okay. So there's lots to say, of course, right? Communication, and as you know, there's physics behind communication. There's many concepts. So the first slide is about parameters. So when you're considering communication options for IoT, there's many parameters that you have to consider. So one is a range. So when we're talking about IoT, we have short range applications, sensors on the body, wearables, and at the same time you have very long distance links. So different ranges can use different technologies. The other one is cost. So I think that's something that we all learn when doing IoT, is that you have cost, you have a business model. You're either paying upfront in some way, setting up the architecture, or you're paying someone for the service. But that you have to consider. And then there's cost of the device and cost of the service. Those are two different costs. Then you have multi-hop, which means one device talking to the other, and you have battery consumption. Again, you might be happy with a device which you need to replace the battery every couple of months, or you might have some applications where the sensors are in the woods and you want them to be running for many years. And finally, you have availability and regulation. We're going to get into that point immediately, but in some cases you need to pay some fees to be able to use the frequencies. And then you have security, of course.
Yeah, I think, and also multi-hop capabilities. Often that is called mesh as well. Aren't when we're talking about the same thing? So
exactly, I would say that was really hot a couple of years ago. Now maybe that's less popular, but I would say in the old days that was really important. So being able to just set up the devices and they would create a network by themselves.
Yeah. And we do have that possibility with the devices that we are working with the PyCom devices, both actually LoRa mesh, and also Bluetooth, of course.
Yes. Exactly. Okay, and then the specific case of IoT is kind of a bit different from what we're used to in terms of kind of computer science. So IoT nodes can accept low throughput. So in fact, most of the applications, I would say, almost all of them require really low throughput. So you're just sending small chunks of information every, couple of seconds or every minutes or every hour. And so I put that in red. So can you think about application where you actually need more throughput? Is that an IoT application or not? So let's see what people say on Discord. In the meantime, let's go to the other 2 points. So delays is another one. So we're not working with devices that require, real-time operation. We're not, acting on like robotic arms or things like that. Third one is sleeping times. So most of these devices sleep most of the time. And then they wake up, they send some data, and then they go to sleep again. So that, again, is kind of special about IoT, right? If you have a laptop, then you're browsing the internet all the time. So again, it's a bit different.
But it's interesting that you put it up this question, because we had that up for discussion last week when we talked about IoT and the definitions. So, and where actually are, like, it's not a very clear boundary.
Not at all.
No.
So for example, wearables or smartwatches, they're measuring all the time. So, and they're probably using Wi-Fi to send that information on the internet. Is that part of IoT? Is it not? So it's, as you say, it's not trivial, right?
No.
I would say in my definition, IoT, they sleep most of the time. Yeah. And they measure something, they wake up, they send the data, and then they go to sleep again.
Yeah, and that's also, I mean, I think that the most applications that people are going to work in this course are going to be some kind of sensor nodes, actually, that are transmitting data on some timely basis.
Every now and then.
In between sleeping, of course.
Yeah. Okay, so heartbeat comes up as an application where you need more throughput. Yeah. That's true. And okay, video streaming like YouTube, I would say that is not an IoT application. So again, we're kind of focusing on this low throughput world of IoT. So there's 3 concepts that I want to kind of really quickly cover, but I think they're kind of interesting in this perspective. One has to do with spectrum. So the spectrum, the frequencies that we use for wireless communications is kind of divided in chunks. So this is the case of the US. I actually looked for the case of Sweden, but I couldn't find a similar map. But anyway, the concept is the same. So it shows that these frequencies they have specific uses. So there's some frequencies that can only be used by ships to communicate with harbors or among themselves. Or there's other frequencies that you can use only for military use. There's broadcast. There's different applications of the spectrum. But the point is that you have to obey to this use of the spectrum, and most of it is regulated, which means that you have to pay the government. You have to pay some fee to use that specific frequency. So the mobile phone operators, they pay lots of money to use specific chunks of frequencies. But there are some specific frequencies which are called ISM bands, where ISM stands for Industrial, Scientific, and Medical Radio Bands, which you can use for free. And in the case of IoT, there's 3 of them. So these, range around 400 megahertz. The other one around 800 megahertz and 2.4 gigahertz. And in fact, 2.4 gigahertz is the same frequency that you're using for Wi-Fi at home. So if you set up Wi-Fi at home, you don't have to pay any fee. You can just use it. You don't have to ask for permission. So these 3 bands you can use for IoT. And again, the interesting part is that you can just use them without paying any fee.
One quick question here is that I have 5 gigahertz on my Wi-Fi router, and I guess most people have. So, and so that's also included in
that's included. It's just below the 2.4. Yes.
Yeah.
But I haven't seen any IoT device that uses 5 gigahertz.
No, I haven't. No.
Yeah. So okay. So those are the 3 kind of bands that you use for IoT. Interesting thing is that if you think about frequencies, they have different behaviors. So think a bit about the FM radio that you listen in your car. You know that if you have a small FM radio, you can just move around the house, for example, and you still pick up the signal. If you consider Wi-Fi, as Frederick, you were saying, if you're using 5 gigahertz, you know that you just move one room and there's no signal anymore. Meaning that lower frequencies have good penetration. They can pass through walls and they can penetrate inside a building quite well. Higher frequencies, like 5 gigahertz in Wi-Fi, they cannot penetrate that well. So again, these different bands have different characteristics in terms of penetration. So this is bands. So we're using 3 bands. Second concept is this one that has to do with power in a wireless system. Okay, so very often people say, or they read about very long links in IoT, and their experience is that they can go really short distance. And they say, how is it possible you reach 10 kilometers and I only reach 100 meters? Well, it all boils down to this graph, which telecom engineers love. In fact, I always joke and say that they have a tattoo, with this picture because they use it all the time. And that actually applies for each and every wireless system, ranging from TV to FM to Wi-Fi to satellites. They all use the same concept. And the concept is that you have a transmitter on the left, which has a certain power, which is connected through a cable to an antenna. And in the cable, you're losing a bit of power. You're dispersing a bit of power. The antenna, in some way, amplifies the signal due to its shape. It doesn't have any power, but it has a shape. So it concentrates all the power in one direction. And then you have a certain path loss. So these wireless systems going through the air, they lose a bit of power. And so the longer is the distance, the more power you're losing. Then on the receiving side, you have an antenna which picks up the signal. Again, it kind of amplifies the signal in some way. You have a cable where you're, again, losing some power. And then you have a receiving, radio. And if the received signal is stronger than the sensitivity, then you're okay. So you're receiving that signal. If it is too low, then you cannot receive the signal at all. And the point is that some of these components you can actually improve. You can pay for it. You can get a better radio. You can get more output power. You can get a bigger antenna. But some others you cannot improve. So the path loss is given by physics. So you cannot pay to get a better path loss. Yeah. And again, sensitivity, depending on the technology, you can have better sensitivity. So those are the parts that you can actually improve.
Yeah, there was a question actually yesterday about the antenna and if it's like the difference between the LoRa and the Wi-Fi antenna of the PyCon boards. And well, they are different lengths. So, and we're very near the area of the frequency and the length and the size of the antenna. Could you elaborate a little bit on that?
Yeah, sure. So antennas, they have to be specific for a specific frequency. So as you said, we're using Wi-Fi on the PyCon board, so 2.4 gigahertz, and we're using LoRa, which is on 800 megahertz. So they have 2 different frequencies. It is also true that 800 megahertz is like a third of 2.4 gigahertz. So meaning that you can still do with kind of the wrong antenna for the wrong frequency. But if you do so, most of the power that you're transmitting is going to come back to the radio. It's going to, in a way, bounce back to the radio, which means that, first of all, you're not outputting all the power in the air. Most of it is coming back. And second, you could damage the radio. So you should always use the proper antenna for the frequency that you're using.
Yeah.
Okay. So this was the second concept. We can just show this in a very short way, just to say that this path loss goes like 1 on R squared. So you see in this picture, it goes down in a certain way. It's quite easy to understand, but maybe we can skip this. Third kind of important concept is something called Fresnel Zone, which again is special about radio. So if you have two antennas, the one on the left and the one on the right, you might be able to see the other antenna with a binocular, for example. And this is the so-called line of sight. So you see the other side, but the radio waves actually occupy a certain volume, which looks like a cigar or a football ball. So
Yeah.
it has, it occupies a certain volume in 3 dimensions.
Yeah.
And this volume has to be empty if you want the transmission to be successful. So you shouldn't have any obstacles. In fact, this is the reason why they put antennas on top of mountains or on hills, because they want to have this Fresnel zone as free as possible. And this zone has to do, the size of the zone has to do with distance. So the longer the distance, the bigger this Fresnel zone. And second, it has to do with the frequency as well. So the higher the frequency, the smaller the Fresnel zone. Okay, so if we want to sum up, you have certain frequencies that you can use for free. You have, the power calculation that you have to do in every, telecom system, and you need to have this Fresnel zone free. Okay. So let's finally move to LP1. So we said that IoT is specific, and LP1 stands for low power wide area networks. So of course we want to have these systems to be low power because they're usually battery powered. So we want to, have the battery last as long as possible, and we want to have the coverage as wide as possible. And as we're happy with low data throughput, it means that we have a high sensitivity, which means that we can detect very low signals, which means that we can go really long range. And all of this is done with the goal of having a low-cost system. And these LP1 systems are using licensed or unlicensed spectrum. So let's see, where do these systems fit in the overall picture? So let's focus only on LoRa and Sigfox on the right side. And then you have GSM, which we all know, and we have Wi-Fi. So let's consider Wi-Fi. So Wi-Fi has a limited range. You can cover maybe a building, few hundred meters, and the data rate is high. So someone was talking about YouTube. So you're throwing a lot of data using Wi-Fi. So you have limited range and high data rate. If we're looking at GSM, GSM has a long range. You can cover, tens of kilometers, if not hundreds of kilometers, and it has a high data rate. Our LP1, LoRa, and Sigfox, they fit here. So they have a long range, but a low data rate. Okay, so that's our goal, having a long range and small data rate. If we consider power and data rate, well, as we all know, Wi-Fi and GSM, they use a lot of power.
Yeah, and just but you make sure that no one, so you notice that actually the X and Y axis has been changed. So if you flip back one and go back again, so now you have on the Y the data rate, and on the X axis that's the range.
Yeah.
So
and now here you have data rate and power.
Yeah.
So again, Wi-Fi, GSM, they use a lot of power. We want to be in this side where we have low power and low data rate. So now if we put the two pictures together and we have range on the X-axis and power on the Y-axis, we have our LoRa and Sigfox, they sit in the lower right side. So long range and low power. Okay, so that's completely different from GSM and from Wi-Fi and from Bluetooth and other protocols.
Yeah, and I do really like these kind. You can find these kind of pictures in actually like this kind of diagrams in different places. So, and I've used actually, I think the same exact slides as you before, but I do like, because there is always a discussion when you're having these kind of courses and we're talking about IoT, is that, oh, I want to, well, a SIM card, and then everything depends on what you're trying to do. So if you want to transmit some kind of like video feed or sound, or if you want to transmit very, very often, so even if it's just a temperature, but you want it like 10 times a second, well, LoRa is most likely not the solution, and Sigfox not either, and not narrowband IoT. So and this is actually a very good way of explaining. So you can't really say that something is better in this picture.
Not
You
at all.
can't point at one point and say that this is the best one. That's not how it works.
We're looking at a specific niche, right? A niche where, again, we want to have long range and low power, and no other technology fits that need. Okay, super. So let's start with the first one. So Sigfox. So there's two players, in fact, Sigfox and LoRa. So Sigfox uses a kind of strategy which is called ultra narrowband. So the signal in Sigfox is really, really narrow. It's really small, which means that being narrow, you can have a very high sensitivity. So this number maybe will not, tell you much, minus 134 dBm, but consider that noise level, RF noise level, is around minus 100 dBm. So a signal using Sigfox is able to decode and to decode a signal which is 34 dBs below the noise level, which is really, 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 really low. But I think the important point is that it's narrowband, it's absolutely low power consumption and low cost. So each message in Sigfox is transmitted 3 times in 3 different frequencies. So the idea of a Sigfox signal is that you're just sending a message and you're not waiting for acknowledgement from
I think that's a very
system.
important
Absolutely.
thing to mention.
Yes.
When you so that you have a very, very dumb
Yes.
sensor. It
So
sends out, it shouts, say, hey,
Yes.
hey, the temperature is 55 degrees.
Yes, exactly.
Yeah.
So all these LP1 systems use the same kind of strategy, right? They're all yelling in the air and they hope that someone is picking up this signal. So Sigfox, to be sure that someone will pick it up, shout the same message 3 times in 3 different frequencies. So this is how it works. The frequency is, again, ISM, so unlicensed. So you can use Sigfox without any requirement of a license. So it's 868 megahertz in Europe, 900 megahertz in the US. But there is a limit in the number of messages that you're sending. And this, I think, is key. So you can send 140 uplink messages per day. So if you divide that by 24 hours, that's roughly 7 messages per hour, which means that, again, roughly you can send 1 message every 10 minutes. So if you're happy with a system that sends, a message every, 10 minutes, then Sigfox is a solution. If you want your data to be sent more often, it's not a solution. You can also send 4 download messages per day, so from the system to your node. And the mobility is restricted to 6 kilometers per hour. So again, if you're thinking about, tracking system on a car, that will not work unless you have a really slow car. Okay, what is the business model? This is quite interesting. So the business model of Sigfox is that they work with mobile operator to install gateways, meaning that if you want to use Sigfox, you don't need to set up any infrastructure. So you have someone that set up that infrastructure for you. And this is, again, quite interesting. It's based on a subscription basis. So you have to pay a certain amount of money every year. I believe it's roughly 10 euro or $10 per year. So it's really, really limited, but still you have to pay certain amount of money.
I think you get. I think they those that PyCom has some kind of agreement. So 1 year, I think.
Exactly. So the device with the devices that you have, you can use Sigfox for 1 year for free. So it's if you want to experiment with Sigfox, you can do that easily. Yeah. Interesting aspect is that you have a kind of a geo localization capability without a GPS. So as they have many of these gateways all over the place, they can triangulate and know kind of where you are. So this is kind of cool. And then you have a roaming capability, meaning that if you design an application for Sweden, you can sell that same device to France and it will work out of the box. But of course, it really depends on the deals that Sigfox has with operators. So this is a map. You see that in some places, the blue places, they do have coverage. The pink one, they're still rolling out Sigfox. So it really depends where you're living. I picked up Kalmar. It looks like you have a good coverage of Sigfox. And so again, if you want to experiment with Sigfox, you can do it.
Yeah, and I have tried it, and it works here. So,
and it works inside buildings as well. I don't know if you experienced that. And
yeah, I've used it at campus, and so I can't say for all buildings, but well, I was inside when I tested it, so
it works fine. Yeah. So that's the positive aspect. Okay, so let's move to LoRa. I think, Fredrik, you shared a presentation about a video presentation about LoRa.
The Things Industries, or well, I think previous to Things Network, isn't it? I think they might have changed their name in this process when they came with the new platform. But yeah, I shared a presentation. I'm not sure how many that have seen it, but that's actually a really good presentation on the LoRa network basics, like what we're going to talk a little bit about now. So
okay, so LoRa is a wireless modulation technology based on a proprietary solution by a company called Semtech. And LoRa is actually the physical layer. So if you have, a LoRa chip, then that's only the physical layer of LoRa. As we see, LoRa 1 provides some more advanced capabilities, I would say. It operates in the ISM bands all over the world. And instead of being narrowband like Sigfox, it is based on spread spectrum. So meaning that your signal is kind of moving in a certain range. So it is trading bandwidth for signal to noise ratio.
Yeah, yes. And maybe we want to explain a little bit what we mean by the physical layer, because this physical layer can't be seen.
Yeah, that's true.
Yeah,
it's a bit similar to what you said about mesh. And you said, we do have mesh in the PyCom devices. And so when you have mesh, or when you have, any other, system, you have the physical layer, which usually makes sure that you get bits from one side to the other.
Yeah. So this is a physical layer, at least Ethernet cable. Correct.
Yes, exactly. Yeah.
So, but now we're talking wireless, and then the wireless we can't see. So
exactly. Yes. Yeah. But on top of that, usually you want to add some more advanced features, like security, like authentication. You don't want your neighbor to be part of your mesh network. You want to be in charge and know who is able to access that mesh. So you want to have these kind of higher level layers on top of your physical layer. Okay. So we said again the frequencies. So LoRa is on sub-gigahertz, so below 1 gigahertz. So again, 433, 868, 900 megahertz. It depends on the country, as we will say. So this is quite interesting. So ISM bands, they are free to be used, but that doesn't mean that they're not regulated. So they still have regulation. You have regulation in terms of the power you can use. And in case of LoRa, you have limits in terms of power and on duty cycle. So duty cycle means how often you can transmit, you can send data. And in the case of LoRa in Europe, we have a 1% duty cycle limitation, which means that your device, your PyCom device that uses LoRa, can only transmit 1% of the time. So if you consider 1 hour, it means that you can transmit 36 seconds in each hour. Okay, so you might think that this is, very small amount, but actually, if you do your calculation, as I'm sure that you will do in the labs, you will see that in 36 seconds you can transmit a lot of data in 1 hour. It's plenty, but still, again, ISM doesn't mean not regulated. You still have, a regulation. So why is it called chirp modulation? It is called chirp because it inspired by radio signals, and you have these two chirps. It's like an up chirp where the signal increases its frequency, and the down chirp in which it decreases in frequency. Not that important, but this is why it's called chirp. I had colleagues which were, singing this chirp and showing how this frequency goes up, but I will, not do that. So, as Fredrik was saying, that the physical layer is, the physical layer, and so in the case of LoRa, you have a preamble, so you have 10 up chirps, and then you have about 2 down chirps, and then you start sending your data. Again, technicality, not really important.
But we just go back to that slide. I think it's
sure.
very interesting because when you talk about the chirp, so what we're actually seeing is that there is a signal that is, well, gliding like this. So, and what the properties of this? This is like a part of the LoRa technology, which is patented, as far as I understand. So
yes.
Yeah, so anyone can use this, but I mean, if you use it without their permission and pay patent fees or whatever, you will get sued. More or less. It's not that it's secret. It
is not that it is you paying for the fee. So when you buy the LoPi device from PyCom, they pay the fee to use the LoRa chip. Okay, it is simply not an open, source kind of chip, right? It's patented. But again, when you buy it, it's simply, you already buy the technology in some way. Okay, but as you pointed out, so this is what you see if you have a spectrum analyzer. So if you put a spectrum analyzer with an antenna, you're looking at what is happening in the air, you would see this kind of pattern. You see some up chirps, the signal going up, then you have some down chirps, and then you have your data. This is how LoRa works. Okay, so then there's many parameters that you can set in a LoRa physical layer, setup. In fact, there's more than 6,000 of them. The combination of all of them. So one is the bandwidth, which is the width of the spectrum occupied by the chirp. The other one is the so-called spreading factor. So the number of bits encoded per symbol. So in some way, it means how spread is your signal. In fact, if you have a higher spreading factor, the communication range increases, and so the radio sensitivity and the signal to noise ratio. But the energy consumption also increases because the signal is more spread, which means that it takes longer to transmit the same amount of information. Then you have the coding rate, the transmission power, carrier frequency. Anyway, the short story is that when you set up a LoRa system, you have to make sure that both the transmitter and the receiver have the same parameters. And in some way, these parameters are orthogonal, meaning that if a friend is using the same frequency at exactly the same time, but has a different spreading factor, you can both communicate without having any interference up to a certain level. Okay, so frequencies, well, we're in Europe, so we're using this 868, but this is just to say that different zones, these are United Nations zones, they use different frequencies. So if you want your system to be working in Japan and you design it in Sweden, well, you're out of luck. You need to have different frequency bands. And so you have to pay a bit of attention in that regard. Or if you buy something from the US, it's the same, right?
And for most cases, I mean, in this course we are in Europe. I guess that actually we might have one student or two that are not living in Europe, but not very many. So
okay, but just to say that there's different frequencies even for LoRa.
But Sigfox, I mean, if you're talking about frequencies for LoRa and Sigfox, is that those can be used? You don't have to think about that in the same way. Or?
Exactly. Yeah. Yes. Yeah. So we were saying about these nodes that they like to shout, right? So it's exactly the same for LoRa nodes. So if you have a LoRa node, here is, node number 1, which has a LoRa module, it has a microcontroller, it has some sensors, some actuators, and, a battery. It will shout its message, and in the packet header, it will say, okay, this message comes from node number 1, and it's for address to node number 2, and this is the message, and that's it. But node number 3 will still pick up that message. Okay, so node number 1 is just shouting that message. So as we just said, LoRa is very basic. It's only the physical layer. So you have to write your application so that you only decode messages coming, in this case, from node number 1.
Yeah.
So
and
there's
now people in the course
work.
might be like, okay, do I need to code this physical layer or
not the physical layer? Yeah. But what you have to remember is that LoRa, if you're using the basic LoRa examples, they're very basic. So you have this kind of, they call it ping pong, right? So you're sending messages from node 1 to node 2, and then node 2 is sending a message to node 1 again.
Yeah, I actually made that application when testing the range. So I made a ping pong device with two Poicom devices, just flashing like on the LED and walking around. And
that's wonderful. But the point is that you can have node 3, which still sends messages to node 1 and 2.
Yeah.
There is no security, there's no authentication, nothing like that. So it's, again, very, very basic. In fact, on top of that, this LoRa Alliance developed something which is called LoRa 1. So LoRa Wide Area Network. So this is a communication protocol and architecture that uses the LoRa physical layer. And that is completely open source, freely available. And they designed to have what is called star of stars topology, which means that you have two different devices. You have end nodes, and you have what they call gateways. We'll get back to gateways in a second. But the idea is that the nodes send messages only to gateways. You cannot have communication from one node to another node. It is just from node to gateway. And there's multiple layers of security. So you have a lot of encryption. Again, we will get back to that in a second. So you can make sure that only nodes that are part of your application can send data to your application. You have encryption, you have frame counters, many kind of technical details to make sure that your network is secure. You have what is called adaptive data rate, meaning that the system, these gateways, they can tell your node, use a specific spreading factor. If you're using basic LoRa, there's not such system. So you have a spreading factor set in node 1, node 2, and that's it. You cannot change it. In LoRa 1, you can change it in a dynamic way. So we said that these end devices, the devices, the modes, they can only communicate with gateways, never directly with other modes. And they have a globally unique identifier, which is called DEV EUI. I don't know, Frederick, have you covered this identifier
we
idea.
haven't gone through these just yet. So that will be more of the topic for the upcoming week. So
Okay.
I think most people this week are on the level when they are like getting started with the hardware. So
Okay.
but very soon you will all know about this.
Okay, but I think it has to do with this general idea of IoT, where we said, do we need to have a unique identifier for a node in an IoT network for it to be an IoT network? And in case of LoRaWAN, you do have a unique identifier, so your node is unique in the world. They have 3 different classes of devices, and essentially the important part is that class 1 is the yelling kind of device, where the node is only sending data. And it has the lowest power because, again, it wakes up, sends some data, and then goes to sleep again. In class B, you have some windows where you can send a message from the network to the device. So you might want to have a class B device if you have, let's say, an actuator or something like that. You want to be able to communicate with the node. And in class C, that's even more. You have this window is open all the time. Okay, so class A, low power, class C uses much more power. So this, I think, is a kind of interesting picture if you haven't seen that before. So it has to do with this architecture. And the way it works is, again, on the left side, you have the end devices. So let's say this device is just sending some data on the air. This data is received by one or more gateways. And these gateways are also called packet forwarders. So they receive a packet in LoRa, in the air, in wireless frequency, and they send that packet using Ethernet or 4G or Wi-Fi. So they essentially send that packet on the internet. On the internet, you have something which is called a network server, which checks if 2 or more gateways have received the same packet. So essentially, the network server removes multiple copies of the same packet. Okay, so if you're just yelling and 10 gateways receive your message, well, the network server will say, okay, I only need 1 copy of that message. I don't need 10 copies. The second thing that the network server does, it sends that piece of information to the proper application server. So you might have different devices on the left sending, temperature and humidity or light or, heartbeat or whatever. And they want to send data to different applications. So this is what the application server is doing. And again, I'm sure that you will see that much more.
Yeah, there is a lot of new words. And then
Absolutely.
I think also one of the big things of getting your head, like getting into the area of IoT, is that you have all these new things. You need to know what a network server is. And a network server, in this case, it's something that receives the data from the gateway and also actually checks that end node is, I mean, you have some encryption going on as well.
Exactly. Yeah. So I think what you should remember about this picture is that these devices yell, so they just send messages. These messages are received in some way, and then LoRaWAN provides the encryption, the security, the authentication.
Yeah, and that's very interesting because, I mean, everything that is wireless, everyone can listen into it. So it's really out there in the open. And you might not care very much about your temperature, but I mean, it might be sensitive data that you are sending. And even if it's not sensitive, maybe security might be an important thing because you want to know that it's actually that sensor that you're receiving and not some other sensor.
All right.
So, and that is also sorted out by the encryption, isn't it? So
absolutely, yeah.
Yeah.
And then as we know that IoT has to do with billions of devices or huge amount of devices, then having this encryption done properly is really important, right? Because again, you don't have one temperature measurement, you have thousands or millions of devices. Yeah. So it's really important. The other interesting aspect about LoRaWAN is that being that a known standard, people come up with devices that can communicate on LoRaWAN without much, I would say, any coding from the final user. So you can go up in the market and buy devices which are ready to be used. So the LOP is fine, of course, it's really good. There you go.
Yeah, there is this is a Dragino distance detector, so it's actually ultrasonic sensor here.
So this device you can just buy, and maybe in 2 minutes you're able to send data on the internet.
As long as you have a low-code IoT platform, which is the topic for next week. But yeah, so there are these. I would say at this moment they might not be very consumer friendly, but I would say that it's not very hard either. So
so that again is different between LoRaWAN and LoRa. So if you have LoRa, you definitely need to code. Definitely, you need to be a coder. If you're using LoRaWAN, you can buy stuff on the market and you can just use it. Okay, so last part of the presentation has to do with again LoRa transmission. And just a few days ago, Fredrik sent me an email and said, look at that kind of strange behavior. I got a message from, where was that from?
This is from Klaipeda to Kalmar. So, and this is actually one gateway in Kalmar, you can see on the map. And on the other side of the Baltic Sea, you have Klaipeda in Lithuania. And this is LoRaWAN. So this is a witness from the super interesting, 320 kilometers.
Yeah, so it's quite interesting because, again, if you read about LoRa, people say 50 meters, 100 meters, maybe 1 kilometer. But now Fredrik gets a packet which is 320 kilometers far away. How is that possible? So I have been researching about that a bit in the last year, and there's many cases. It's mostly anecdotic. So there's this guy in Germany saying, look at that, really strange. One specific day, I received packets from all over Germany, and they're like 180 kilometers far away. What is going on? This is crazy. And then there's even some other guy would use Sigfox, and they put that information on Twitter. Say, look at that, 1,300 kilometers far away. I have a gateway in Italy. I have a car in Spain, and that GPS from the tracker has been received in Italy, 1,300 kilometers away. How is that possible? And the reason has to do with something which is called the troposphere, which is about 10 kilometers above the Earth level. So normally the radio waves, they go a bit beyond the horizon. So you have the optical horizon here, which is again the line of sight, some place you would see with the binocular. But the radio wave can go a bit longer range. But then there are some specific cases, which usually happen in the summer over the sea, where you have an inversion. So you have temperature and humidity, and the kind of mess up and these higher levels of the troposphere, and the signal from your radio kind of bounces over this troposphere. And in some really specific cases, you have what is called a duct, which means like a kind of a special layer where the signal bounces a couple of times, and it can go really, really far away. And in fact, this is it. So normal is the green, then you have super diffraction, and you have this ducting. So signal bouncing on the Earth and then on the troposphere. And that is exactly what happened in Fredrik's case just a few days ago. So this signal, which was sent by maybe some really small antenna, really small device in the home of someone, just bounced on the troposphere a couple of times and then reached your gateway. And this is kind of really interesting. And we published 2 papers about that, and it's kind of interesting. And just to tell you that over 300 kilometers, this is the Earth curvature. So there is no way you can reach, even if you have a very high mountain from Lithuania to Sweden, you should have, super high peaks on both sides. So this is not line of sight. It's definitely something strange. So the Earth is not flat. That is the other.
There are people that don't agree. So
yes, exactly. I know, but yeah. Okay, and then the really final one, because again it has to do with LoRa, and I think it's quite interesting, is that in the last, I would say, year or so, some university they have launched some satellite, this small satellite, this CubeSat, really, really small satellite, which send LoRa message from space. So I would say it is not very useful. It is just sending beacons, sending messages, but it's really incredible, how far you can go. In fact, there's, almost 2,000 receivers on the Earth which receive these signals from space, and they do that, all the time. So the satellites move in a very quick way. So you get, 2 or more passages over the same point all over the Earth. And there you go. There's 6 of them running, again using LoRa, and you can receive them with super low cost ground stations. So the interesting aspect here is the cost. It's 25 euros. So you have a ground station which can receive LoRa signal from space with 25 euro. This is kind of mind blowing. It's just incredible. And those are just 2 packets that I received, I believe, yesterday from my ground station. And you see the distance here, it's 800 kilometers. So we were saying that LoRa is a long distance. The range is long. It is super long, not only long. And this other guy just next to my, always in Italy, 1,229 kilometers. So with this low cost technology, just thanks to the modulation, over 1,000 kilometer LoRa link. It's quite incredible. So this is just to say that it's really, really a powerful technology, and I'm glad that you're going to use LoRa in the course. And I think that's all from my side, Frederick.
Yeah, there has been actually a pretty vivid discussion on in the Discord channel. So let's say first, thank you very much for the great presentation. And you are already in the Discord channel. So you might, if you want to ping Marco directly, you might just like ping him.
Sure.
But you're that generation which answers email faster than Discord, I guess. So, so maybe an email might sometimes be a better way. So that's great. Maybe we could spend some time and see if there is any questions from the people. From all the students here. There is there any, I got it, is there a website showing the LoRa coverage and where I can use open LoRa networks? So there's already been 2 answers, the Things networks and then explorerhealy.com. But that's also a good question because there are some initiative. You have the Things networks mapper. I think there isn't it a mapper server?
It's called Ttn Mapper. Maybe we can show that. Do you want to show it, or I can?
Yeah, please, you can share your screen. You've already.
Okay, there you go. Yeah. So this is Ttn Mapper. So Ttn is one of the options that you have in using LoRaWAN, and I think you're going to use Helium, right, Frederick?
Yeah, we are not going to be limited, but we are going to use both of them, as I see.
So people that use Ttn or Things Network, they go through this mapping exercise. So they again, they measure the signal level in different places, and then they kind of map the coverage. So you haven't done that.
Actually, the gateway which we have on campus is now down for firmware upgrade. That was just 2 weeks ago. So they might be very quick on actually updating the data. But
anyway, there's places like in the Netherlands where the whole country is covered by TTN. And okay, it's also, you know, smaller countries, but with this TTN, again, you see the coverage. Of course,
but this depends. This coverage map depends on community crowdsourced data. Actually, you need to run your own mapper. Am I correct?
So this means that if you don't see your place covered by TTN mapper, this doesn't mean that there is no coverage. It means that there is no one that went through that exercise. This is my place, and yeah, again, I think there's different ways to show the coverage as well. Yeah, so in fact, that is something that I have proposed to Frederick, and maybe some students will be interested in having an kind of IoT coverage application. So my point is that TTN only shows the things network coverage, and then you have Helium. So I think it would be really interesting to have a system which shows both TTN and Helium and, you know, some other systems coverage. And Sigfox coverage, for example.
Yeah, and this is the Helium, mappers.helium.com, which is also based on the same kind of what you said, is that, well, it's crowdsourced, so people need to run their own devices. Helium is a much newer network, I would say, so I don't think it's mapped that well, but actually we have done a little bit of mapping ourselves, and I'm responsible for much of this, I would say, in Kalmar. But this is really not telling you, it's only giving you an indication of that, okay, someone has been mapping here. So if you want to go online and look at the coverage map, both TTN and Helium, which is the biggest open, I would say, LoRaWAN networks, because there are many like closed LoRaWAN networks which companies might set up their own gateway, and well, obviously they have a LoRaWAN network, but you won't be able to use it. And then we have this in many municipalities in Sweden, and I am sure of that the same thing is in all over Europe, and they are not open. You might get access to them as maybe as a company or research institute, but often not for like individuals. But Helium and the Things network are the most, like they are both open. You can just register your application and send data right away. It won't cost you nothing to almost nothing. It's super duper cheap. So.
And again, as you were saying, Frederick, at the beginning, there is no one single solution, right? You might want to use, you know, GSM. I had some applications with air quality in Africa where we had GSM. So that was the only option, sending SMSs. There was no 3G, so we could only send SMSs. And at the end of the day, it was quite cheap. So these SMSs are quite cheap nowadays. So that might be a solution.
And also, I mean, there are. I actually saw that. I think it was PyCom that actually made an announcement today on LinkedIn that they had an alliance now with ONCE, the data network provider, with ONE and SCE. And I think they sell, it's at €10 or something like that, and then you get 10 years of connectivity. So and actually, that's cheaper than Sigfox. But you also get something else. So it's really that trade back. But a SIM card might be super cheap.
But it is power hungry.
Yeah.
So using GSM is always power hungry. So it's not the best solution if you're sending data very often. And then you have satellite. So I showed this example of LoRa sending, LoRa signals from space. But now there's few operators which provide satellite connectivities for IoT, and they're not that expensive. So in that case, you don't really care about infrastructure. You're just sending data to space, and that's it. So there's Lacuna Space, which I'm sure you know, which again uses LoRa from the Earth to the satellite. And then there's, I believe, a French company which provides the same service.
Yeah. What kind of, if we were to think a little bit about the future? So I mean, we LoRaWAN has existed for about, could we say, about 10 years or
something like that? Yeah.
Yeah, and it now it's gained a lot of traction. So we still see new things coming out, and it's like new things happening with LoRa. But like 5 years from now, so is there any like, or what's your view on that? So
I think it as we said at the beginning, it has to do with money, right? So who pays at the end?
Yeah.
So TTN started from this idea that you're paying in a way because you're buying the gateway and you're making that gateway available to people. That is one business model. I don't know if it works fine or not. In Helium, I understand it's the final user paying a small amount of money to send data over the network. And in Sigfox, you have these, $10 per year or something. So I think that's the, kind of main issue, right? So the one that will survive is the one that has the best business model.
Yeah.
And the one that scales up, that's the other one. Because we're now talking about one PyCom device. Maybe you have, 20 PyCom devices in the lab, but we're really far away from thousands of devices or, millions of devices. You're going to spend lots of money if each and every device is, 10 euro to send applications. So, yeah.
And then let's see, they're talking about Zigbee and Fred and such as well. So should we elaborate something about that? Because now we're talking about low power networks. So
yeah, sure. And in fact, is that I think the mesh aspect that we discussed about at the beginning is one of these kind of technologies which are like, under the radar for some time, and then they come up again, and then they go under the radar again. But I think that's really interesting. So if this IoT has to grow in a sustainable way, probably mesh is a really good solution, because then you can add more and more nodes, and the network will kind of grow in an organic way. Yeah. And so all these links that they have been, sharing about, Thread and the new Zigbee and so on, I think there's something that we should keep an eye on, definitely.
Yes, I guess that we have covered. So actually, we got a very specific question here. Can you recommend a cheap gateway that works with the version 1.1.1 of TTN? So, but a cheap gateway. I can actually elaborate a little bit about, because I bought a very cheap TTN gateway just a week ago, because I've been looking at it and I thought this might be the time. So I bought this one. But I can say right away, I don't really recommend it, because it's not updated for the new stack. So it doesn't actually work at this moment. I'm sure it will, but at this moment, this very moment, it won't. Otherwise, I would actually recommend the Pygate.
Exactly. I was going to say exactly the same thing.
I was looking around, but I actually gave that away yesterday to a colleague in the Vecco lab that wanted connectivity. But the Pygate, it's a really neat little device, and you below 100 euros and you have a gateway.
Yeah,
and much below, I would say, at least.
Yeah, and it's quite a low power as well.
Yeah.
So we measured power consumption, and it's quite low power as well. Yeah.
And then there are some like these Dragino gateways, which is in the range of 100, 150 euros, I believe, even actually maybe below 100 euros. But I don't have any personal experience of working with these, but I'm sure that they do have the same Semtech chip as everything else, and it's just a Linux firmware on board. So it's probably
the kind of professional ones are the Arak ones, and they're quite interesting because they provide some additional capabilities, like you can put devices in a blacklist in some way. So if you don't like that device, you just put it in a blacklist. And the other thing is that if you don't have connectivity to the internet, you can still run the network and the application server on the gateway itself, which might be interesting for some kind of remote sites.
Yeah, and also you can install, I mean, when you're talking about network server, I got a very valid question like earlier up in the Discord channel, is what's the network server? Is that cloud or is it what is it? But yeah, you could say that it is cloud, because it mostly is, but it doesn't have to be cloud. It can be also on a Raspberry Pi, and you can actually run the network server on the same Raspberry Pi as you have your radio module on. That's possible as well. So, but often when we talk about network server, we think cloud infrastructure. So,
yeah. I worked on a project about accessing Ttn from Africa, from African universities. Yeah, because again, that server is in Europe, and in fact, it's in Ireland. It's based on a Microsoft Azure server. Yeah, and so it kind of takes a bit to go from South Africa up to Ireland, but actually it didn't take that long. It took few milliseconds from the academic network, so it didn't really make huge difference. Yeah.
No. And this is one of my. This is also connected to the Things network, and this is a Ttn Gateway. So just to give you an idea, and this is more of it's an indoor gateway, but that's like, let's say mid-ranged priced, so 300, 400 euros, something like that. But this does it does the same thing as a Pi-gate. So I wouldn't recommend any of you buying this one instead of a Pi-gate for this course. And also the added benefit with the Pi-gate is that you can actually tweak and do something else on the board as well. So you can do that on that as well, but then you need to get into the Ttn version of their Linux, play around.
Yeah. So if any student is interested in projects that have to do with LoRa and LoRaWAN, I have plenty of ideas. So please feel free to contact me either here or on Discord or email, and we can work something out.
Yeah. And that's really good, because and I can vouch for that. Marco he always have an idea, and he always have the contact as well. So you always know someone. Oh, I know him, and so that's great. I think so. We haven't missed it. If you haven't gotten your question answered, and we might have missed it, just ask it again before we close the stream. So because I'm.
There was a really good question about large LoRaWAN deployment, and I think there was an answer about DHL and the port of Rotterdam, and in fact that was what I was going to suggest.
Yeah, and I think there are some interesting business cases. I think there will be more like business focused. So both you and I are in academia. So, but we do have some upcoming lectures which also have maybe more the application focus, like the business perspective. So we will perhaps hear more about that later. I guess one would get most of this core working with. Yeah.
Thank you.
Yeah, that's great.
That's great. Yeah.
That's great. But it seems that people are relatively satisfied. It might be that the football game is occupying most people that are not here, which is a bummer. They weren't able to move the football game. So
we asked, but they said no. Right?
Yeah, exactly. Yeah. So I missed the goal for this. It's from Parameter. So we're happy that you're here. So. But in that case, we might say goodbye for now, and thank you very much for tuning in, and thank you very much for the questions. And we will put the learning material for the presentation out on the CoursePress site. I will update later on. Please keep in touch in Discord. So Thank you very much.
Okay, thank you. Bye-bye.